record the notes as we go through, just in case you want to go back and rewatch them again later on, see something that maybe you missed the first time, whatever works for you. So I hope that all of you guys had a good Thanksgiving break as well, got to take a little bit of a break from the school stuff and maybe focus on recharging, relaxing a little bit, and getting ready to kind of finish out term 2 here. Also, I do not want to alarm anyone, but today is December 1st. We have officially entered the last month of 2020. Hallelujah. Cannot wait for this one to be over. So we've got 3 more weeks of school left. And so I've got the rest of this week, the rest of next week, the last week, which ends on the 17th. And then we will be off for a couple weeks for Christmas. So we have a couple different subjects that we're going to try and cover and hit in these last couple weeks. And then kind of wrap everything up with the big series of review sessions and a final exam during that last week of class. So that being said, let us go ahead and get started here this evening. So let's see, you gotta do this, and then do this, and then, all right, there we go. Took me a second to remember how to use the Google Meeting again. All right, so if you remember, maybe kind of look at some of the videos that we did last couple weeks. As we got towards the end of the week before Thanksgiving break, we were talking about these electrons and their electron shells, how they get mixed and combined together with those homogeneous and heterogeneous mixtures and the pure substances and all that fun stuff. And we talked a little bit about how we can form chemical bonds between the 2 different substances. And that's what the question about was yesterday, was all about that ionic versus the covalent bond, the transferring the electrons versus sharing the electrons together. So today we're going to do a little bit of a turn. Instead of focusing on the specific kind of structure of atoms, we're going to talk about what happens when we do take different atoms or different substances and chemically combine them together. What sorts of reactions do we get when we try to combine different matter, different substances? So we are talking about chemical reactions in class today. These things that happen when we take different chemicals, different matter, and cause them to change or react with each other and become something new. All right, let's see. There we go. There's my little pointer. Hold on, where's it there? All right, so chemical reactions. What are they? How do they work? What are some of their different properties? That's the stuff that we are going to be talking about tonight. So chemical reactions are all about changing substances. So when we start off with a certain substance, and then it undergoes a chemical change in order to form new substances. So hopefully this sounds a little bit familiar to you. A couple weeks ago, we talked about chemical changes, physical changes, chemical properties, and physical properties. So chemical changes are essentially just chemical reactions. So if you remember from a couple weeks ago, chemical change is what happens when we start off with one set of chemicals, one set of substances, and then end up with something new, something different that was not there before. So some chemical reactions that are going on around you every single day, possibly without you even realizing it, include things like growth. So this little caterpillar down here is not going to stay a caterpillar forever, right? First, he's going to eat these leaves and grow bigger and bigger and bigger. And then eventually he's going to build that cocoon and go in and change into a butterfly. So not only is the change to a butterfly, but also just the growth of a caterpillar, the energy that the caterpillar needs to do all of that comes from chemical reactions happening inside its stomach. Just like you probably used to be a lot smaller than you are now. But over time, you've grown, you've developed, you've added new muscles, you've grown out your bones. Some of your bones have fused together. Your organs have gotten larger. All of that is due to chemical reactions happening inside of your cells. Ripening is another form of a chemical reaction. So if you've ever grown tomatoes before or seen like tomatoes growing on a farm, you may know that they start off as sort of this bright green color, but if you leave them on the vine for long enough, eventually they'll change color and become the nice bright red that we all have learned to love about tomatoes. They do that change due to a chemical reactions. There are chemicals inside of the fruit and the skin of the tomato that over time will cause it to change from green to red. Same thing happens with your bananas, that maybe you buy them from the store and they start off as pretty green, similar to these tomatoes. And if you've ever eaten a really green banana before, you know it doesn't taste that great. It's kind of starchy and chewy. But if you let it ripen for a little bit, a chemical reaction happens inside of the banana where some of the starch starts to break down and turn into sugar instead. And that chemical reaction, not only does it cause the banana to become a little bit sweeter and a little bit more chewy to eat, a little bit kind of more squishy, but it also causes the skin to turn yellow. Then, if you leave that banana on your countertop for a couple weeks, it's going to get really brown and the inside's going to get kind of gross and like a sickly sweet kind of taste and really brown and super mushy. That's because now that reaction has gone too far. We've converted too much of the starch into sugar molecules. And so we don't really have that structure left for the banana. And that change also causes the banana skin to turn brown. So this ripening, this color changing on the outside and the flavor changing on the inside, all of that happens due to chemical reactions inside of the food. Similarly, when food is decomposing, that means that there is lots of bacteria or protists or fungi that are growing on the food. And essentially, they're breaking down the particles that make up the food and turning it into particles for themselves, turning it into energy for themselves. And so they use it similarly to what we get when we eat food, only they are breaking down dead and decaying food. But it's still the same process. We start off with one set of substances, the food itself, and it gets changed into new substances, the energy and the food for the bacteria and the mold and fungi. Burning is also a very common chemical reaction. So when this wood is on fire, it starts off as like the big blocks of wood, right? But then as it burns, over time, you see a lot of smoke come off and go up into the air. And then you're left with that kind of fine, silty ash down at the bottom. That is a chemical reaction. So the wood is chemically reacting with the heat and the oxygen in the air in order to produce heat and light in the form of fire, and smoke is a form of the gas that's coming off in the form of carbon dioxide. And then the ash on the bottom is kind of what's left over after the reaction happens. So we start off with one set of substances. We end up with a new set of substances. And that's what tells us that a chemical reaction has occurred in our mouth. matter. All right, so when a chemical reaction is going on, there usually is going to be some sort of sign, something that's telling you, hey, this new stuff that I'm making, it's different than the old stuff that I had before. So things like bubbles appearing in your reaction is a potential sign that a chemical reaction is going on. So I think when we talked about chemical changes, I mentioned the example of if you like drop an Alka-Seltzer tablet in water, then all of a sudden it starts fizzing and the bubbles start coming up and making that kind of fizzy froth on the surface. That is due to a chemical reaction between the tablet and the water. That's what's creating all those bubbles. So if you're getting bubbles because you took some water and you're heating it up on the stove and it starts boiling, that is not a chemical reaction. That's just the water going through the natural process of being converted from liquid water to gaseous water, which is like water vapor. So boiling is not a chemical reaction. When we talk about bubbles appearing, we mean you're not heating up the substance, you're not adding a whole bunch of heat or energy. You just combine a couple different substances together, and all of a sudden they start fizzing and bubbling when they were not doing that before. On the flip side of this, instead of bubbles appearing, which would indicate a gas has formed, you could also get a solid forming. And in science and chemistry, solids that form due to a chemical reaction get the fancy name of a precipitate. So if you combine two liquids together, and then all of a sudden you have this new solid in your glass, in your beaker, that would be a good sign that some sort of chemical reaction is happening. Because before, you didn't have a solid, and then now, all of a sudden you do. You have something new, something different that was not there before. A color change happening is a good sign that a chemical reaction is going on. Like we mentioned earlier with the fruit, when fruit is ripening, if it's a tomato, it might color change from green to red. If it's a banana, it will color change from green to yellow to brown. And all of those color changes are due to chemical reactions happening inside of that food. Again, by color change occurring, we do not mean that you had some water and then you put some purple Kool-Aid mix into the water, and now all of a sudden you have a purple mixture in your water. That's not really the kind of color change we're talking about, because you added something purple to something clear and you ended up with something purple. That's kind of what you would expect to happen. There wasn't really any chemical reaction that happened there. But if you take like a clear liquid and you take another clear liquid and you add them together and then all of a sudden those turn purple, that would be a good sign of a chemical reaction. You didn't expect them to turn purple, but all of a sudden some sort of change happened down at the atomic level, and now that liquid looks purple when it didn't before. A temperature change is a good sign of a chemical reaction. So you combine some substances and all of a sudden they start heating up or they start cooling down. So an example I like to use, which works a little bit better from when I lived in Ohio versus when I lived down here. If you've ever been somewhere cold before during the winter time, you may have seen at the store, they have these little hand warmer packs where you buy them, you take them home, and then the next day when you're ready to go outside and it's like 17 degrees outside, you take one of the little packets and you kind of squish it up and then you put it inside of your glove. When you squish it up, you introduce some chemicals to each other that naturally react and will heat up. And so when you put this in your glove, after a couple minutes, your hands are nice and toasty, even though it's super cold outside, because of this chemical reaction inside of the hand warmer. Before, the chemicals were separated, but when you squished down the little packet, you combine them together, and they started to go through a chemical reaction where they got hotter. Light being given off is another really good sign that a chemical reaction is happening. Like we just talked about earlier with the fire, the fact that the fire produces light is a good indication that we have a reaction going on where energy is being given off from the reaction in the form of light. And then also, we could get a new smell or a new taste being created that was not there before. Again, this works really well when we talk about the ripening examples. So a green tomato tastes a lot different than a red tomato, and a gross brown banana tastes a lot different than an underripe green banana, right? So when we get new smells or new tastes being produced that we didn't notice, we didn't observe from before, that could potentially be a good sign that some sort of chemical reaction has occurred. So just some pictures of some examples. This guy over here is some bubbles that are being formed in this kind of glass container due to a chemical reaction happening. And this jellyfish down here is producing some of its own light through a process called bioluminescence. Essentially just a fancy word for living creatures that can produce their own light. So things like this jellyfish here or a firefly is another really good example of a creature that can do this. They have special proteins inside their cells that break apart certain molecules, and when they do that, their reaction produces light. So that's why some of the tendrils on this jellyfish are glowing. That's why the fireflies are able to light up their butt when they're going and flying around during the nighttime. It's because of chemical reactions happening inside of their bodies, inside of their cells. And one of the side effects of those chemical reactions is that light gets produced. So, chemical reactions, all about changing one set of substances into a new set of substances. And there are a bunch of different ways that could be evidence that a chemical reaction is occurring in your substances. All right. Like I said, it should sound a little bit familiar to when we were talking about chemical changes in substances a couple weeks ago. But does anybody have any questions so far about chemical reactions or some of the signs of a chemical reaction? Anything anybody wants me to go over again?
So is there only 6 signs of a chemical reaction?
There are some more, but these are far and away the 6 most common.
Okay.
So there may be certain chemical reactions that don't exactly do one or more of these, but these are kind of the ones that are the most obvious and the most easy to notice when they do happen.
Okay.
Good question.
I was just asking because of the assignment you gave us today. It says,
Yeah,
what are
exactly.
the 6 signs of chemical reaction occurring? So I just wanted to make sure it was those.
Yep. So these are the main 6.
Okay. Thank you.
That you guys should know. No worries. All right. So, like I was saying, chemical reactions are essentially just the process of chemical change. So we're taking one or more original substances and changing them into new substances. So when we do this, we can write it out sort of kind of like a math equation where we have our original substances on one side of this arrow, and then our new substances on the other side. Now, this is science, which of course means that we have to give specific names to the original and the new substances. So our starting chemicals, our original chemicals, the ones that react together, are called the reactants. As you can tell, scientists, very creative and artistic people. We have the substances that react together. Let's call them the reactants. So those are our original starting materials, are our reactants. This is the chemicals, the substances that we are starting with. So they're going to react together. And then at the end of it, they're going to produce something new, something different. So again, the substances that are produced, scientists said, let's call those the products. So the products are our final results. These are the things that we end up with at the end of the chemical reaction. So a chemical reaction is a change in which one or more substances are converted into new substances. We can also say that as a chemical reaction is a change in which one or more reactants are converted into products. So we're taking our reactants and we are turning them into our products. So whenever you see a chemical reaction written out like this with the big arrow, the reactants are always going to be on the left side of the arrow, and the products are always going to be on the right side of the arrow. We're taking our reactants and we're turning them into products. So a really good example of a sort of everyday chemical reaction that you may not have thought much about before is the reaction of photosynthesis. So photosynthesis is what we call it when plants make their food, make their sugar using sunlight. So everybody knows that you put plants in the sun and give them some water, and that's really all you need to do because they make their own food. Photosynthesis is the chemical reaction that actually makes the sugar for the plants. So it's going to look kind of big and scary at first, but I promise I'll walk you through each piece and you'll see that it is actually an overall pretty simple equation. So here is our photosynthesis equation. Notice we have our little arrow right here. So over on our reactant side, we have carbon dioxide, that's CO2, and some H2O, which is water. So we're starting off with the chemicals carbon dioxide and water. When we add the energy that the plant gets from the sun, that carbon dioxide and that water turns into a big chemical called glucose, which is basically just sugar. So C6H12O6, meaning that glucose is a big molecule that has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, all bonded together. So we make some glucose and we make some oxygen, and these guys are our products. So we start off with carbon dioxide and water, and we create glucose and oxygen. So the glucose is what goes into the plant, and it'll actually be used as energy by the plant later on. The oxygen is what's given off by the plant back up into the air, and this is actually what we breathe in order to stay alive. So we breathe oxygen and give off carbon dioxide. Plants absorb carbon dioxide and give off oxygen. So reactants over on the left-hand side, CO2 and H2O. Products, what we're making, are over on the right-hand side, C6H12O6 and O2. So again, this is a quintessential chemical reaction because we are starting off with two substances and we are ending up with two different substances, right? There's no carbon dioxide over in our products. There's no water over in our products. Instead, we've turned our reactants into something different. We've turned them into something new. We've taken that carbon dioxide and water and turned it into glucose and oxygen. So that's kind of the first and second main things to keep in mind about chemical reaction is that we're creating new substances, and our original substances are called the reactants, and our final substances are called the products. The other really important thing to know about chemical reactions is that in chemical reactions, the way they work is that all they do is rearrange the atoms. What this means is that we can't add in or take away any of the atoms on the reactant side and add in or take away any on the product side. So what this means, for an example, is that over here on the reactants, if we go atom by atom, you can see that we have some C's, some carbons, we have some O's, some oxygens, there's two right here and one over here, and we have some H's for hydrogen. So C's, O's, and H's are the only atoms that we have on the reactant side. What about if we go take a look at the product side? Well, we've got some C's, just like in the reactants. We've got some O's, there's some right here and some over here, just like in the reactants. And we have some H's, just like in the reactants. So on the reactant side, we have C's, O's, and H's. And on the product side, we have C's, O's, and H's. So there's nothing new in the products that wasn't there before, right? We didn't all of a sudden get nitrogen and N added in somewhere. And there's nothing that we took away from the products that wasn't in the reactants, right? We didn't all of a sudden lose all of our H's. They're still there. So are our C's and our O's. So the only thing that happens in chemical reactions is that we rearrange the atoms into new configurations, into new molecules. So in this case, we added some H's to our C's and our O's, and we took the H's away from the water, so it was just left with O. So we rearranged the atoms, we moved the H's and the O's around, but we didn't add or take away anything. All right, so in chemical reactions, we can't what's called create or destroy any new atoms, right? We can't add or take away any atoms. All of the different atoms that we started off with in the reactants, we have to have in the products. So if we have C's in our reactants, there have to be C's in our products. If we have O's in our reactants, we have to have O's in our products. If we have H's in our reactants, we have to have H's in our products. If we have C's, O's, and H's in our reactants, then the only things that we can have in our products are C's, O's, and H's. So that's what I mean when I say that chemical reactions rearrange atoms. That we're not adding anything, we're not deleting anything, we're not getting rid of anything. We're just moving around exactly how the atoms are connected to each other. All right, any questions about the atoms being the same, not being created or destroyed? Any questions about kind of our little photosynthesis example right here? All righty. So we know that in order to have a chemical reaction, we have to start off with one set of substances and end up with something new. We know that there are a couple different ways that we can tell that chemical reactions are happening, like the bubbles and the color changing and the light and heat and stuff like that. We know that our starting material is called reactants and our ending material is called products. And we know that we can only move around the atoms in a chemical reaction, so we can't create or destroy any of our atoms. We have to have the same set of atoms in the reactants as in the products. So in addition to the atoms being the same, we also have to have the same energy being conserved throughout the chemical reactions. And essentially what this means is that whatever energy that you put into the reaction has to be equally created by the reaction. So whatever energy is there, you can change it into different forms, but you can't end up with more or less energy than you started with. So again, just like with the atoms, how I have to have the same atoms at the beginning and the end, we also have have the same energy at the beginning and the end. Only in the case of chemical reactions, we can transform that energy from one form into another. So whatever the total amount of the energy is in your reaction is going to be the same at the beginning as at the end. It just maybe will take a little bit different form. So a really good sort of basic example of this is with a simple light bulb here. One of the kind of like old school ones that gets really hot if you leave it on for a couple minutes. And that's because there's electrical energy that's going into the light bulb. So this is like why it has to be plugged into the wall socket, right? To get that electricity. So if we say that there's 100 units of electrical energy going into that light bulb, then that light bulb is producing two different things. It's producing light and it is producing heat. So we are transforming that energy from electrical energy into light energy and heat energy. And in the case of the light bulb, there are 5 units of the electrical energy that are being used to produce the light and 95 being used to produce the heat. So this would be like more like the kind of old school, like not super efficient light bulbs. Nowadays, they have light bulbs that are a lot better, where they don't need as much energy to go to the heat. But with the older ones, those light bulbs put off a lot of heat, but together, it's the same amount of energy that we got from the electricity, right? We got 100 pieces of electricity, and we transformed them into 5 pieces of light and 95 pieces of heat. So that's what we mean when we talk about energy being conserved, is that whatever energy goes into your reaction, you have to have that same amount of energy at the end or being produced by the reaction, but it can be transformed into all sorts of different ways. So one going back to our photosynthesis example that we were talking about a little bit ago. In photosynthesis, I mentioned that you need energy from the sun in order for the photosynthesis to happen. And so when the plant gets that energy from the sun, it changes the light energy. It changes the light energy into chemical energy. So the sugar that's produced, that glucose molecule, that C6H12O6 guy that we were looking at earlier, that is going to be used as energy for the plant later. So we've converted solar energy into chemical energy. So ideally, that energy is going to be used by the plant. But if that energy goes into, say, some fruit, and then we eat the fruit, then we get to use that chemical energy for ourselves. So the energy that powers our body comes from the food that we eat. Which again, if we're eating plants, was originally energy in the form of light. Only now it's been converted into chemical energy for the plants, and then it gets converted again into chemical energy for us. So we can change, we can transform the type of energy that we have, but it still has to balance out the energy that goes into the reaction versus the energy that is given off by the reaction. All right, so there's kind of two different ways that chemical reactions can use energy. Either they can produce energy and give it off into the environment, or they can absorb that energy and use it to build structures as part of the chemical reaction. So there's kind of two main types of reaction that deal with energy that we're going to focus on. The first one is called an exothermic reaction. So exothermic, exo is, I believe, a Latin prefix that means like going out or giving off. And then thermic is like thermal, so that's related to energy or heat. So an exothermic reaction is a reaction that releases energy. It adds energy, it gives off energy into the environment, usually in the form of heat. So exothermic reactions tend to produce a lot of heat. So the area around the exothermic reactions will get hotter because the energy is being released, right? If you have a fire going, like this little match right here, if you have a fire going, you don't need to stick your hand directly into the flames to know that it's hot, right? You can get within a couple feet and the air around the fire is getting hot because burning things and combustion is a very exothermic reaction. So the area around this reaction will heat up due to all this energy being given off. So digesting food is a good example of an exothermic reaction. So when we digest food, we break it down into smaller and smaller pieces. And when we do, we're producing energy for ourselves, not just in the form of chemical energy that gives us the ability to get up and move around and stay alive, but also in the form of heat. So as you may know, especially if you've been taking your temperature a lot during this whole pandemic situation, the inside of the human body runs along at about 98.6 degrees Fahrenheit. That's kind of like your baseline level of heat. You may notice that we tend to live in areas that are not 98.6 degrees Fahrenheit all the time, especially like this past weekend and yesterday. It's pretty chilly outside. So our body has to produce a lot of interior body heat in order to keep that 98.6 degrees temperature up. So one of the major ways that our body does this is through digesting food. So the heat that gets given off by this exothermic reaction, we use in order to make sure that all of our cells and organs are functioning properly. Decomposing things. So when things like bacteria or mold or mushrooms break down dead bodies, decaying logs, stuff like that. That also is exothermic reaction. So they're breaking down, breaking apart those big molecules into smaller ones. And then obviously combustion reactions like lighting wood on fire or the reactions that occur inside of your car. So the reason why your car is able to run, and you may notice that after you get home from being out and doing some groceries, put your hand over the hood and it's pretty warm, right? You usually don't want to put your hand like right on there. That's because there's a whole bunch of exothermic reactions going on inside of your car engine that's burning that gasoline and keeping your car running. So any sort of combustion is going to be a very, very exothermic reaction. It's going to produce a lot of heat. So a lot of exothermic reactions may give off light as well. Not all of them, but especially the ones that we're most familiar with. So like burning fire or burning oil. When we burn it, it produces flames, and those flames give off light. So giving off light is also a good sign that an exothermic reaction is happening, but it does not have to be, light does not have to be produced in order for it to be exothermic. All that has to be happening is that energy in some form is being released to the environment. That is what you need to be exothermic. So set a match on fire, it starts burning, it gets hot, it lights up. Everything that tells you that this is a very exothermic reaction. Heat and light are being produced by the reaction. They're being given off to the environment. So it is exothermic. So what about the opposite? What if we don't give off energy, but instead we take it in, we absorb it? This is a type of reaction called an endothermic reaction. So again, thermic meaning energy or heat, and then endo meaning like going into is, I think, the Latin form of that word. In an endothermic reaction, we are absorbing energy from the environment. We're using the energy in the environment in order to produce something. So the reason why we're absorbing energy is that we're building larger molecules, larger chemicals. So those covalent and those ionic bonds that we were talking about at the end of last week, a lot of times you need an initial input of energy in order to get those atoms to bond together, right? In our photosynthesis example, we started off with carbon dioxide and water, which are pretty small molecules, but we're going to put a whole bunch of them together and build up a big glucose molecule. And so because we're building this larger molecule with all these bonds, we need to absorb that sunlight energy. So we might be absorbing light, like in the case of photosynthesis, or we might be absorbing heat. So there are some endothermic reactions where they'll actually cause the area around them to get cooler because they're absorbing so much heat energy, it's actually dropping the temperature of the surrounding area. That's not as common as the heating up that happens in exothermic reactions. So not all, or I think not even most endothermic reactions cause an area to get cooler. Like in photosynthesis, the area around the plant is not cooling down because of the photosynthesis, but some endothermic reactions do result in this kind of cooling feature. So So again, in photosynthesis, we have the light from the sun. So the sunlight energy is being absorbed by the plant and being used to create large sugar molecules. So we're making lots of chemical bonds between the carbons and the hydrogens and the oxygens that we're getting from our reactants. And we're creating these new molecules, these new glucose sugar molecules that we're able to make because of the energy we absorbed from the sun. All right, so just to quickly review, exothermic reactions producing energy over the course of the reaction. Energy is being released out into the environment, usually causing the temperature to heat up in the surrounding area. Endothermic reaction, energy is being absorbed by the reaction. We're using energy usually to create new and bigger chemical bonds. Doesn't necessarily have to get colder, but we have to be absorbing energy somehow, using the energy in order to help power some sort of aspect of the reaction. So exo being released, endo being absorbed. All right, any questions about exothermic or endothermic reactions? Anything from those two guys that you want me to go over again? All righty, so just to review everything really quick. So we have our chemical reactions are when we take one set of substances and change them into something new, something different that we had before. When we do this, we could create bubbles. We could cause a color change to happen in our substance. Maybe light or heat will be given off or absorbed over the course of the reaction. But all of those are signs that some sort of change has taken place. Our starting material in a chemical reaction is called the reactants. And then our final material that's produced, our last substances, are our products. We can't get rid of or add in any new atoms to our chemical reaction. We can just rearrange around the atoms that are already there. So if we have C's, O's, and H's on our reactant side, we have to have C's, O's, and H's on our product side. No more, no less, just a combination of those same atoms. We conserve energy throughout the process of reaction as well. Any energy that goes into the reaction will have to be created by the reaction. But we can change what type of energy that we get. We can change it from light energy into heat energy, into chemical energy, into electrical energy, all sorts of different changes as long as we have the same overall amount of energy. And then we have those final two different major guys that we talked about, the exothermic reactions that release energy into the environment, and our endothermic reactions that absorb the energy from the environment. And that is everything that you should need to know about chemical reactions. So let's take a quick look at the homework. The assignments for today and tomorrow should be pretty short and straightforward. So for today's homework, today's assignment, I just want you to list out the signs that a chemical reaction is occurring. So we talked about these on the notes about the different things that might be produced or might change as a chemical reaction is going on. I just want you to list out what those signs could be for your Tuesday assignment. And then for your Wednesday assignment, that's going to be going up tomorrow morning and be for your attendance credit tomorrow. Also, pretty short and sweet. I essentially just want you to compare and contrast the exothermic reactions and the endothermic reactions. So what are the characteristics of exothermic reactions? How can you know that a reaction is happening is exothermic? And then on the flip side, what are the characteristics of an endothermic reaction? What's going to be happening during the course of an endothermic reaction? So that is your daily assignments for Tuesday and Wednesday of this week, the first 2 days of December. Cannot believe that it is here already. All right, so does anybody have any final questions about any of the chemical reaction stuff that we talked about, anything from the notes, or anything about the Tuesday or Wednesday assignments?
No, I don't have no questions.
All right, thanks, Gabriella. Well, if you ever do think of a question or you have something that comes up that you want some help with, please always feel free to reach out to me. You can text me, you can email me, you can leave me a question on the Google Classroom, and I will do my best to get back to you as soon as I am able.